Hi everyone. This lecture is an introduction on, or rather, a course outline what we will be discussing in the series of lectures on CMOS OPAMP design. Now we have previously I have mainly discussed about an ideal OPAMP and circuits built using ideal OPAMP. So you might quickly recognize circuits here which are shown here. The first one here is a voltage follower. The circuit shown here is an inverting amplifier, and this one here is a non-inverting amplifier. We also very briefly discussed a circuit called the switched capacitor circuit, which we said it has certain advantages compared to a conventional, especially when you want to realize filters. We said switched capacitor circuits find great, I mean, it finds significant, they offer significant improvements over a conventional continuous time filter. They have their own limitations. In fact, we will understand from a circuit point of view what are those limitations. So the circuit shown here, this one here is a trans impedance amplifier. The output voltage depends upon the input current times the gain of the circuit, which is the trans impedance R. Now, in this course, we will actually look at what are the different possible circuit realizations of this ideal circuit, which we have so far assumed to be an ideal circuit element, which is the operational amplifier. The fundamental questions we will be answering is, now if you look at the first circuit, can I apply any voltage and expect the circuit to behave as a voltage follower? Is there any limitations on the range of voltages can I apply? If there are limitations, what dictates those limitations? So voltage range, what is the maximum and minimum input and output voltages? So that's something we will look at it. And this question has to be answered by looking at the circuit realization of these op-amps. The next one is speed. Will this op-amp, all the op-amp circuits we have discussed so far, will they give me a faithful amplification or faithful voltage follower operation for any frequency? If I just, let's say I fix this amplitude and then keep increasing the frequency, will they give me the same gain, or how does that gain change? So that behavior, we'll answer it in fact, properly analyzing this op-amp circuits under the discussion of frequency response and bandwidth. And we said fundamentally when you want to design an op-amp, it's just a high gain amplifier circuitry. We will see what are the different ways in which we can get those high gains, and what are the advantages and disadvantages of those different realizations of an op-amp circuit. The other important parameter, which we have not discussed so far in our previous course on microelectronic circuits, is noise. How does one size an operational amplifier for a certain noise? Okay, what does noise of an operational amplifier depend upon? What are the origins and what does it depend upon? As a designer, how can you control the noise? Similarly, how can you control the speed? So speed, again, there are two kinds of specifications for speed. One is a nonlinear specification, a large signal specification. The second one is a small signal specification, which is typically given in terms of bandwidth. There are some close relationship between the two, but not always the case. So that's why we define both nonlinear, a large signal and a small signal parameter to characterize an op-amp. So when I say to characterize an op-amp, to tell how fast the op-amp operates. Okay, so there are some metrics which we will use to characterize this operational amplifier. Similarly, I've spoken about voltage range. What is this voltage range? What are the range of voltages for which this amplifier will behave as an amplifier, input and output? Okay, applies to both input and output. And also, we will talk on very important voltage, which is the common mode voltage. In fact, we will see there are some architectures which we will prefer because they will have less reliance. The output swing will have less reliance on common mode voltages. So far we haven't spoken when we discussed operational amplifier circuits. We just assumed the positive terminal to be at ground. Okay, so that op-amp is actually a dual supply op-amp. So which supplies usually vary from plus VSAT to minus VSAT. So we picked an intermediate voltage which happened to be 0. But in most practical circuits, they are all unipolar supplies. So your minimum voltage will be 0 and max will be VDD. In that case, you will choose a common mode voltage. You will have to properly choose this common mode voltage. How does one choose it? And does it have any impact on the output swing? So we will study all those behaviors. In fact, when you look at a circuit, all these things will become very clear. Okay, so if you, for example, if you look at this operational amplifier circuit, which is used in a switched capacitor circuit, in some half cycle, so we said in switched capacitor circuit, in some half of a cycle or a fraction of a cycle, the input and output are shorted. So this terminal and this terminal are shorted. So your output will be equal to VCM itself for a very short duration. So under these conditions, how does one ensure that I get the maximum gain, bandwidth, and voltage swing out of this op amp? Does it depend upon the common mode voltages? If so, how does it depend upon it? All those questions will be answered when we look at the circuit realizations of these op amps. Then we will talk about another very important thing, which is another class of amplifiers called precision amplifiers. So most operational amplifiers will come with what we call as offsets. Okay, so we have always assumed when we analyzed op amp circuits that the inverting and non-inverting terminal voltages are nearly the same. But in practice, they will not be the same. And the difference between the two is what we call offset. So there will be some finite offset between this. And what effect does that have on the output? So sometimes you want to very precisely measure the output voltage. So for example, in a transimpedance amplifier, you want to sense this current very accurately, even small changes in the current very accurately. Your output voltage is given by the common mode voltage plus I in times R, right? It's just the DC voltage here is VCM. It's negative feedback circuit, so DC voltage will be VCM. Then this current I in is going to flow through the resistor, so output voltage will be I in R plus VCM. In the presence of offset, you will also have an extra term appearing here. This will corrupt. So now let's say you have a circuit, or the goal of the circuit is to measure the changes in this current. Okay, what is the minimum change in the current that you can measure? That is limited by offset, because it's getting added to offset. There will be some error in measurement. So those circuits are called precision circuits, which will have very low offsets. So how does one design this? What are the techniques to reduce offsets in operational amplifiers? So that is another important topic. We'll also look at the origin, the source of these offsets in operational amplifiers, and how to reduce them. Okay. And finally, in fact, a good chunk of this course we will spend on fully differential operational amplifiers. We very briefly introduced the idea of fully differential circuits in the introductory course on microelectronic circuits. But here we will look at operational amplifier circuits which are built. I mean, a fully different operational amplifier circuits which are built using this idea of fully differential amplifiers. So you will realize fully differential operational amplifiers itself. See, the op amps which I've shown here previously, input is differential but output is single-ended. But we will later see in fully differential circuits, they again offer this huge advantages of common mode rejection. Fully differential operational amplifiers offer supply, any common mode signal will be fully rejected. So that's one big advantage of fully differential circuits. Okay, so we will talk extensively about the fully differential operational amplifier architectures. And there are some new problems in fully differential amplifiers, which is the output DC. So that was not really a big issue in single-ended op amps. Generally, the output DC is set either by the input common mode or by the input voltage itself. In voltage, for example, the input voltage here, output simply follows the input voltage. So this node also, input voltage also changes, or I mean the inverting input voltage will also change depending on the input voltages. So all the three node voltages are very clearly defined in most of the circuits. But in a fully differential circuit, we will see when I start discussing fully differential amplifiers, the DC amplifier, the common mode voltage at these two nodes are not clearly defined. You have to very clearly define them. Okay, so you need some circuitry to do that, and that's called common mode feedback. And how does one decide what DC value to choose that? And similarly, what input DC value should we choose for this op amp circuit? So which is the input common mode? If you recall from the previous semester's lecture, we said if your operational amplifier has to give you any gain at all, the input transistors should be biased in saturation. So it needs a minimum common DC common mode voltage for it to operate. What is that DC common mode voltage? And how does one dictate what is the DC common mode voltage at the output terminal? Okay, so that's the other important thing which is not present in a single ended circuit. Okay, so that's a very important topic called common mode feedback. So we will introduce a circuit which will precisely set the DC voltage at the output of a fully differential amplifier. Again, the same, we will perform the same analysis. We will look at the speed, how fast can this op amp react to changes in the input. Okay, and we will also look at the different applications. So the way in which we will look at this course is that we will see in what application the op amp is used. First, I will discuss the different architectures, how to realize large gain, what are the different circuit realizations of an op amp that one can build to realize a very large gain. So the fundamental goal is to build a large gain. So that's what op amp is. Op amp is a high gain amplifier. What are the different ways of building it? And what is the best architecture of an op amp that an engineer can pick for a specific application? If you're building an ADC, which amplifier, which architecture will you go for? If you are building a DAC or a high precision amplifier, what kind of an architecture will an engineer choose? Okay, and what is the not only architecture, but what are the currents, and what is the area, and all those constraints will be we will try to discuss in a good detail. Okay, so that's the introductory. I just wanted to briefly discuss an outline of what we will be discussing on this introductory course on CMOS OPAMP design. Okay, the next lecture I'll start with the different both single-ended and differential realizations. What are the different ways of realizing uh, high gain amplifiers? Okay, so I'll quickly take you through the DC gain and the DC operating conditions like common modes and output DC voltages. So those things you will be able to very easily follow because we have discussed all most of that on the introductory course on microelectronic circuits. Then we will slowly go to other parameters, speed, accuracy, and all of that. Okay, thank you.